Alright, calculators, here we go. We're doing lesson number 2, numbers 4 and 5. Let's get started to the point. Alright, Marge and Homer are exercising on stair-stepping machines. The total number of floors Marge takes is modeled by blah, 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 where t is measured in minutes. Find the total number of floors Marge has taken in 9 minutes and the derivative of m at t equals 9 minutes. So this is the total number of floors. That's what this function is. The derivative, remember, is just that instant slope. So we're going to have to do a really, really close calculation of slope, and we're also just going to need to figure out the value of this. So how many floors has she taken? The number of floors equals m of 9. We got to plug in 9. So let's type this into our calculator here. So I got a calculator. I'm going to clear this stuff just so we can see it. Okay, so I'm going to go to my equations here, clear this one out. So let's go ahead and put in that crazy equation we see. Now it says t, but we're going to use x because that's the variable that we have in our calculator. So we got 4.5 times, we got x plus square root of x. So the square root button's right here above x squared, so I got to press second and then x squared. And then we put the x there, so I'm going to close that off, and then I got to close it off again because that x goes into the square root, and then we need another parentheses. Alright, so there is our function. Let's graph it. Now something to keep in mind, wow, that goes way up there, so we need to change our window. Our x is still going to be at 0. We can't have negative time, but right now it's going up to 10 or 9 minutes, so let's go up to 10, just a little bit past it. And then we have this going on here, y minimum, y maximum. It looks like we can't go less than 0 floors. But already this is way off the screen, so let's go up to at least 10. See what we get there. We're still way off the screen. Wow, she climbs fast. So let's go back to our window and let's go up to 100. 100 floors. Now, since we're going all the way up to 100, we're not going to count by ones. We're going to count by tens. So I'm going to change the y scale to 10. So we'll count by tens there. All right, that looks a little bit better what we're looking at. Now, notice that even though we have this graph, and it looks like there's 10 marks vertical and 10 marks horizontal, it's really counting by tens going up and down. So that's like 100 units vertical and 10 units horizontal. Okay, so let's calculate the value at 9, because that's what we're trying to figure out here. So what's the value when x equals 9, when our input is 9? Y is going to be equals 54. So 54 floors. That's a lot of floors. And what are the units? Okay, so she did floors. We need to figure out the slope. Well, in our picture, if you guys remember, our y, our up and down, is floors, and our horizontal, which is the bottom of a slope, like x, in this case, is minutes. So it's going to be floors per minute. We'll see that in a second. So let's calculate this slope. Let's do that. All right, there we go. Okay, so if I clear this and I can calculate that instant slope, I'm going to have to do the slope of that function. So I'm going to use that y1 thing that we've been doing recently. So I got to go to vars, yvars, function, and y1. That's the function that we're using in this case. Now we're going to plug in, 9 for our input. Now I'm going to subtract for the other one something very close to 9. So I got to go to vars, yvars, function, y1. This time I'm going to plug in 9 point, let's do 3 zeros. 1, 2, 3, and then a 1. Okay, and then we close off our numerator. Now we got to divide by the difference between these two numbers, which is going to be 9 minus 9.30. 1, 2, 3, and a 1. Close it off, and let's see what we get. 5.249, I guess you could say. So the slope The derivative is 5.2499. I think there's two nines. Floors per minute. That's your units. Because it's the change in y over the change in x, though. Vertical change, the rise over the run. And this is our rise units over our run units. Homer's workout is modeled by this. T is measured in minutes and measured in floors per minute. H of T, oh, whoa, look at this. This is interesting. Find the rate, pardon me, let's take that part back. Find the rate at which Homer is working at t equals 9 minutes and the derivative of h at 9 minutes. What is this measuring? Alright, something weird's happening here because Homer's workout's modeled by this where h of t is measured in floors per minute. So this is a speed or a velocity. This is a rate. It is a slope. So that's kind of weird because we don't have to find the slope by taking that whole measurement of the slope. All we got to do is plug it in. So h of t is equal to the slope or the rate of Homer at time equals t. Okay, it kind of says that, but that's exactly what's happening. So if we're trying to find the rate of Homer at this time, then we don't have to find a slope. We just plug it into t. So that means h of 9 equals the rate at time equals 9 minutes. So we just got to plug in that value. All right, so let's go back to our calculator here. I'm going to show you guys a trick with, well, not a trick, just a method with doing multiple functions in the same one. So this is going to be 10 minus, now it says t, we're going to use x. So x to the 3 halves. Well, I got to group that 3 halves in order to type it in correctly. 3 halves divided by 10. Okay, so we got that. But I don't want to look at the first graph anymore. I don't want to see it. I just want to see the second one. So to take that one off, all I got to do is press enter over the equal sign. Now I can look at just the second graph. So I'm going to look at this graph. See what Homer's doing. Whoa, he's kind of staying low there. Yeah, but that's just a rate, keep in mind. That's not the same thing as the first graph that we're looking at. So now we need to calculate that rate at time equals 9. So that means we got to calculate the value, not the slope, because we're already given a function that's a rate. Okay, so this, we press 9, press equals. So h of 9 is 7.3 floors per minute. Now, here's the interesting part, and this brings in some physics, I guess you could say. But when you find the rate of a rate, when you find the rate of your velocity, how fast you're changing, and you find how fast that's changing, that's actually acceleration. So the rate of the rate, which is also like a second derivative, actually I'm not going to say that, we'll get into a rate of a rate is equal to the acceleration. It's how fast is his rate changing that. That's really weird to think about, but we'll get used to it eventually. It's the acceleration of Homer at time equals t. Right, let's give ourselves a little bit more space here. I'm going to scroll down. Still do got to find the slope again, so let's go ahead and do that. I'm going to clear this page, clear. We're going to go back to this one. I'm going to re-enter this. Actually, no, I'm going to do it from scratch. Let's do it from scratch. We got to go to vars. Whoops, not tangent. What am I pressing? Clear. I want vars. Why vars? Now remember, Homer is not the first one. He's the second one. So we're going to click on Y2. So we want Y2, and we want again around time equals 9. We're going to subtract y2 of 9.001. So we're going to subtract vars, y vars, function y2 of 9.0001. We're going to divide that by 9 minus 9.0001. There's the change in the vertical and the change in the horizontal there. So let's find it. It's -0.45. So this equals negative 0.45, I think 07 or something. 00. Now here's where it gets a little bit different in the units. It's not floors per minute, it's floors per minute, or per minute squared. Acceleration is always going to be, or not, well, pretty much always going to be something, your units in the bottom are squared and your units in the top stay the same. Alright, let's look at number 5. We're doing really well here. A tire is punctured by a nail. As the air leaks out, the distance d in inches between the rim of the tire and the road. Okay, so we got a tire, and we're talking about this distance right here, this distance. So that's decreasing. It starts at 7, and in the end it's at 2.75. Values of t and d are given in the following chart. Approximately how fast is d changing? Okay, so in other words, what's the rate of d, or the slope of d? So we got to put in another function. I'm going to this time put it on y3. So, wait a second. Do we even have a function? We don't have a function. It says approximately how fast is it changing. Alright. Well, if I'm looking at time equals 10, then I got a window that I'm really looking at. It's right here. 10 and before it and after it. So I'm going to this page. Oops, take that back. Now I'm going to also copy and at around 6. We don't have anything after, so we're just going to use 16. And 14, and right before it. Alright, so we got these two things going on. This one's going to help us find that one. This one's going to help us find this one. Okay, so if I wanted to find the approximate change, then what I'm looking at is how much is the y values, or the vertical change, compared to the horizontal change. And this is really t and d. And that's backwards. I did that backwards. But we're looking at the horizontal and the vertical changes, because the horizontal is as we go across the axis in time, and then the vertical is that output value, the d. So how do I figure this out? Well, it's the same thing as finding any slope. So I need to find the difference between these two numbers. This is our vertical change. And then I need to find the difference between these two numbers here. Now I could do it between 8 and 10 and 10 and 12, or either way like that, but I like to go a little bit on each side just to get a better overall picture of what's happening around 10. Excuse me, it's kind of like averaging the slope before it and after it. So if we look at this, that means that our horizontal change is going to go in the bottom. If we look at the change in the vertical over the change in the horizontal, that's what slope is. And in this case, the horizontal is 12 and 8, so that's a change of 4. And on top, it's going to be 4.21 minus 4.77. Similarly, over here, we got a horizontal change and a vertical change. So we're going to have 2.75 minus 3.98 over 16 minus 14. So we need to make those calculations. And let's see what we come up with. So 4.21 minus, so I got to graph and clear out of this. Here we go. So let's do this. What do we have? 4.21 minus 4.77. So we got 4.21 minus 4.77 divided by, and the change in the bottom is going to be 4. We could do that in our head. 12 minus 8 is 4. Okay, and that simplifies to negative 0.14. Negative 0.14. The other one, it's 2.75 minus 3.98. I didn't put parentheses in there, so I'm just going to calculate that and then divide it. I'm going to divide that by 2 because that's the change in the bottom. And that gives me negative 0.615. So this is negative 0.615. So right here at time equals 10, negative 0.14. The other one's negative 0.615. And does it say use units? Well, it doesn't really, but it would just be inches per minute. Inches per minute. Let's see what else we have. Do I have anything else for number 5? Oh, that's end of lesson 2. Check. Done. Happy face. Yeah, yeah.